Okay, let's start talking about the structure now of flames. As you know, things would be relatively easy, and it is, for example, if you work in atmospheric chemistry where chemical reactions take place over, meters or miles. In combustion, it's not like this. Everything takes place on very short distances, which we call fronts, and which makes the life of people who have to compute these things miserable, because the size here that you can see for a flame front is extremely small. There are quite a few people who worked on that, and mathematicians actually have been interested in this structure, and we'll talk about that. And most of you should have followed the course of Moshe Matalon, so you know that you can do a lot of math on that. I will not go into the details, but I will need to summarize these things are in need for CFD and also for turbulent combustion modeling. So just a few examples here. This is a classical Bunsen flame. You see the flame front here. The flame front is actually much thinner than what you see here. This is a radical which lives also in the burn gases. I need to say a few words because I won't talk about it later, about detonation here. You know that basically the mathematical problem which we face here is the following. We have some unburned mixture which is ready to burn, and we want to burn it, and we ask ourselves which kind of states can we find for that? Are there first multiple solutions? One of the specificities of combustion is that it's a field where you can have multiple solutions for the same problem, which is unpleasant. So before you go into the analysis of the structure of the flame front, you can write conservation equations between the left side and the right side. That's a classical exercise. Many of you probably have done it before. I will just remind you how this works. You will write the continuity equation, the momentum equation, and the total enthalpy equation. And you will write conservation between state 1 on this side and state 2 on that side. So you write that the mass flux is conserved, the momentum, of course you have the state equation. You combine all of those and you can prove that the ratio of pressure between the two sides is linked to the ratio of density and to the Mach number of the flow here, which is also the speed of the front, because if you are in the reference frame of this front, which is a planar front, then you have to go at the same speed as the speed of the front itself. If you write the conservation of enthalpy, you write an equation like that one, and then what you can do is to look, for example, at this first equation, and you can plot in the diagram, which is the ratio of pressure. So this is pressure in the fresh gases, pressure in the burn gases, and this is the density ratio, density in the fresh gases, density in the burn gases. This thing is just a line in this diagram depending on the Mach number. The second relation is the conservation of enthalpy, and if you suppose for the moment that enthalpy can be written as CPT, you can construct this line here, again, in a P2P1 as a function of ρ1 over ρ2 diagram. If you have no heat release, you have a curve like this one. If you have heat release, you have the curve like that one. And so the possible states now that you can have for a front like this one have to match this curve plus the lines I've shown you before, so that in the end you end up with two kinds of solutions. It's more complicated than that, and if you have followed the code of Moshe, you know that. But if you look at these Chapman-Jougay lines, basically you end up with saying that one solution is to have a detonation where the Mach number is larger than 1, that the ratio of pressure is very large. And one solution is to have a deflagration when the Mach number is much less than unity and the pressure ratio is of the order of unity. And those are the two flames you find in the real systems. One of them is called deflagration. So it's basically a system where pressure is almost constant, and the speed here is typically extremely small. C0 is the sound speed of the order of 400 meters per second, and SL is going to be the flame speed, and you know that for most hydrocarbon air flames, this is going to be 40 centimeters per second, approximately, at ambient room temperature. For the detonation, it's quite an opposite system. Here, the speed is going to be larger than the sound speed, typically 1400 to 1800 meters per second, and the ratio of pressure is going to be huge. So detonation is not what I'm going to discuss during this course, even so it's an important field. It's really a case of safety issues or weapon issues. For most flames that you find in gas turbines or in rocket engines, you should be in this regime, which is called deflagration. Now note that this simplified analysis is based on a global balance between 1 and 2. I didn't even mention kinetics, so you cannot do that to find ultimately what the speed will be. If you would like to know exactly if you are in a detonation or deflagration, you need to integrate, of course, kinetics, which I didn't do. But at least we know that there are two possible solutions to our problem. A consequence also that we'll use in a few minutes, if you look at a deflagration and you reuse this equation to write the pressure jump between the left side and the right side of a flame, you find it's related to the flame speed here multiplied by these quantities. Those are the density in the fresh gases, the ratio of densities of fresh and burned gases. And if you look at classical flames, you find this is of the order of 1 Pascal. So in other words, when you look at the deflagration, pressure is constant. And in many cases, actually, you can even forget about the momentum equation. You don't even need it. And we'll use that when we develop theoretical models today or tomorrow morning. We won't even use the momentum equation. You will need the momentum equation if you want to find the pressure, but otherwise, you can forget about it. It means also that when we need to use the state equation, we can say that P1 is equal to P2 for deflagration. You can forget about the pressure dependence, and that will give you a simplified state equation at every point. And we'll use that in the theoretical part. Now, the important thing to realize is that all this analysis assumes that you have a planar flame front. The people who started studying flames, they wanted to look at steady fronts, planar, because if you are sitting in the reference frame of this front, it becomes a 1D problem, which is independent of time and dependent only on one coordinate. Unfortunately, nature, like always, doesn't do what you would like it to do, and these fronts are unstable. They never remain, well, almost never remain planar, and we'll talk about this later, and Moshe has been describing that last year for you. Most fronts will not remain planar. They will start developing structure, even the detonation do, the deflagrations do too, and it will make our life miserable again, because we have to care again about a new problem here, is that these fronts do not remain stable. Of course, I don't want to talk, I said, in detonations in solids. In solids, the detonations can go even much faster, but if you don't do weapons, you don't care. So that's my case today. An example of applications. Detonations and deflagrations are found in multiple applications. This is an example of detonation. Detonation is something usually you don't like to do, except if you're doing weapons or very specific engine like the propagating detonation wave engine here. And sometimes you have detonation systems where you don't want to have them. Typically in a piston engine, you can have what they call rumble conditions, where combustion, instead of being a deflagration as it should, becomes a detonation, and that lasts about one cycle, okay? And that's the end of the engine usually. So detonation is something you would like to avoid in most cases. Deflagration on the other side is what we do in gas turbines or in piston engines. And as I said before, in that case, you should not have any shock waves, you don't have pressure changes. Everything happens almost at constant pressure. And this is what we'll talk about. Now, the trick about deflagration and detonation is that these two worlds, unfortunately, are connected. You cannot decide you're going to do only deflagration. In some cases, deflagration can become detonations. And that's an unpleasant situation like this one, which is a long tube here, which you ignite at one end, and then this thing starts as a deflagration and ends up as a detonation. All these movies are produced not by labs, they're produced by labs, but they are paid for by insurance companies, because these things kill people, okay? And so insurance companies do an amazing amount of test cases where they try to predict what's going to happen to the building. The problem here is simple. If you imagine, I will talk about that Wednesday probably. If you imagine this is a building with multiple stories and you ignite this thing, if it's a deflagration, you will of course kill everyone there. But since pressure is constant, the building will survive. If it's a detonation, you will kill everyone there. They are dead anyway. But the building will survive. The building will, okay, so if it's a detonation, the building also will go away, okay, in which case you will kill everyone. So the objective of these companies is to design buildings in which an accidental release of gas followed by an accidental explosion will stay as a deflagration wave and not become a detonation wave. Because if it's a detonation, you will have much more problems. This is a problem in oil system. Companies like Total, for example, are very worried about that. if you look typically at refineries, and you look at the number of veins you have everywhere on this system, of valves, and you look at the probability that one of them is leaking, you conclude that there's always a leak somewhere in a place like this. There's always a place leaking. So these things are quite, they happen. If you look at the history, you will see a lot of accidents of that type. One of the things that science tells us is that the best situation to avoid going to detonation would be to have no obstacles. I will come back to that in a few seconds, but if you put obstacles in a system like this, you make things much worse. This is a movie actually of an experiment done in Norway for us, for Total and for CEFRC, when we ignite a flame here in a system which has obstacles in there. And I will play it again. You see initially the flame is really laminar, so it's propagating like a deflagration wave, very slowly, 50 centimeters per second. Then it finds the first obstacles, it starts wrinkling, then the second one, and then suddenly it goes much faster and goes almost to detonation. This one does not detonate yet, but it's almost there. So you see here, the blue zone is the laminar flame, starts wrinkling here, and then suddenly, shoo. You can even see acoustic waves bouncing here in this box, and of course this is what you want to avoid. So it's possible to go from deflagration to detonation, and it's not something that you would like to do in most cases. There are a few engines in which we try to work in this regime, but normally it's not something you do. Okay, a few words about flame regimes now. As I said, it takes three to burn, A, B, and temperature. If you don't have all of them together, you will have no flame. So the premix flames, you just mix A and B, you just need temperature, and you can burn later. And the diffusion flames, you will actually inject A and B in the burner. They need to mix and burn at the same time, which makes our lives more complicated. The premix flame regimes, as I said, are split in two. If you are lean, below 1, you have something which is cleaner, because if you are on the rich side, you are basically releasing unburned hydrocarbon in the burn gases. You are wasting your fuel, so you don't want to work in this regime. In practice, you have what we call flammability limits. All of you have heard about that. You can make a premix flame work only in a limited zone here of occurrence ratio. If you are too lean or too rich, it won't burn. So I said you don't want to be above 1, so the good domain will be that one. But in practice, in the gas turbine, this is even too large. Here, when you are close to stoichiometry, you make too much NOx because you are too hot. And you know that NOx is really going much faster when temperature is high. So the good domain in a gas turbine would be somewhere in this region. This is the place where you would like to have your fuel and your air burning and reacting. In practice, most of you know that. You don't want to have a premixed system when you wait for combustion to take place, okay? Because that's very dangerous. So in most cases for industrial applications, you use diffusion flames. Even so, we know that they are less efficient, less clean, but they are much less dangerous, which is an important aspect, because when you store these things separately, there is no possible ignition. A classical picture here of a premix flame, blue, short, and a diffusion flame here for the same system, long, lazy, and yellow here because you are producing soot. So this is nice for a candle in an engine. Of course, you don't want to use those flames. You want to use these flames. So in practice, what you need to do for most applications is you want to store reactants separately, but then you want to burn them as fast as you want. That means you need to premix them at the last moment if you can. So that means that in many devices for combustion, what you will see is a fast mixing system somewhere. And this fast mixing system controls the efficiency of the burner. So let me give you an example here again, which is very important for gas turbine combustion today. This is a classical injection device for a gas turbine. So you have here a swirler when you inject air, and there's a rotation movement here. Here you inject kerosene, droplets, and this system, its goal here is to mix these things, and the combustion chamber is here. And quite often, these systems, probably 10 years ago, were identified as polluting too much. So people said, to make them better, it's like when you cook, you know, it's better to mix the eggs and all the sugar before you put them in the oven. So here, if this is the oven, you should mix these things better before you inject them here. So what do? You just add a tube called a mixing tube. The idea of the mixing tube is that give them more time for air and droplets to mix, evaporate, so that when you go into the combustion chamber, you get something which is better mixed, efficiency will be better. And as always, flames don't do what you want. And I will show you why in a second. So the idea behind this is the following. I will anticipate a little bit, but normally you should know these things. So the zone that you have here when you inject the fuel is a very rich zone. You have a lot of fuel here, and air is on the other side here. That means that if we plot the stoichiometric line, it will look like this one. And that means there will be a zone here where you will have a stoichiometric region in the combustion chamber. So the flame will be stabilized here, and it will reach very high levels of temperature. So you will have a hot zone here, about 2500 K. That means you will produce NOx. And once you have produced it, it's too late, you have to keep it. So that's not a good idea. So the idea of this mixing tube is that if you put the mixing tube here, the stoichiometric line will remain here, and at the outlet, you will keep mixing. So the very rich zones will be diluted with more air, so that at the outlet here, you will have a more homogeneous mixing and something which will be much more lean. In that sense, when you will burn this lean mixture, you will have lower temperature and lower NOx. So this is what the engineers imagine when they build a system like this. Now in practice, it does not necessarily happen that way, because now you have this mixing tube and this idea that here you inject, here you mix, here you burn is a nice one, but the flame now could find out that basically if you have a mixture here, the flame could come back. We call that a flashback, and flashback happens, and when flashback happens, it basically kills the injection systems here. An example of a very old LES we did a long time ago of a system like this. This is a SNECMA injector. We're going to compute only one side of it. I just want you to see the results here. So this is typically the stoichiometric line, this is the reaction rate, and this is the temperature. So basically the flame stays here where it should be. You inject, you mix, and the flame burns here. The important thing of these systems, again, is that if you modify a little bit the operating conditions, for example, in that case, if you go to a lower power, you decrease the flow rate of air, you decrease the flow rate of fuel, then the flame might decide that it wants to go to another place. Like in this case here, you will see we are decreasing the fuel and the air flow rate, and the flame decides now that it wants to sit here. Of course, it's a simulation. It's not necessarily the truth. The truth is here when you look at the injector. This is the experiment. You find a big hole here, and we know that this is usually due to flashback. So flashback, again, is one of the consequences I mentioned this morning. You want to optimize flames. Every time you want to optimize a flame, you have to expect problems. They don't do what you would like them to do. Now, another classification of flames which I need to introduce now. We have talked about premix and diffusion flames, but there is a second way to look at flames, and it's confined or unconfined. The academic world has been working on unconfined flames for a very long time. Why? Well, because it makes sense to start with the simplest prototype of flames that you can find in nature. So typically, if you look at all these flames here, including the Sandia workshop, those are jet flames. You just take a hole, you inject gas, and it's burning in open atmosphere. No wall, no swirler, no nothing. And you need to do that. But in practice, if you look at the useful flames, they are always confined. If you have a flame burning in this room, you cannot use it for anything except light. If you want a flame to produce something that can be power or it can be heat, it has to be in a box. So all the flames that you need to study in practical cases are confined. Well, does it make a difference? Well, it does make a difference for CFD. Because if you study an unconfined flame or a confined flame, the needs for the CFD are very different. The first thing is when you look at the unconfined flame, you have no effect of the geometry in accelerating the flow. So typically, you have no need to account for very strong velocity changes. You don't need to account for the walls, and you don't need to account for acoustics. And you will see that acoustics are a problem in many cases. And in the CFD code, it means also that you need to mesh a geometry like this. I know many of you are doing PhDs, so you know about meshing. You know that at the end of the PhD, there's maybe about 1 year to create meshes that you cannot talk about, but it's a big issue. So if you need to mesh this guy here, it's basically a square. If you need to mesh this one, it's another story, okay? And when you go from unconfined to confined, the world is changing in terms of CFD. So typically when you're meshing simple, what I will call unconfined geometries, you just need to put regular meshes, what we call IJK meshes. That means the node here, its neighbor is known, is I minus 1, and the neighbor on the other side is I plus 1. But this cannot be done for a geometry like this one. Here you need to go to unstructured meshes. There's another difference also, is that when you write DNS codes for a geometry like this, it's quite easy to go to high order schemes. What you call high order is the precision of the scheme. You can use a 4th, 6th, 8th order scheme. That's easy. Well, easy. It takes some time, but it's reasonably easy. When you go to an unstructured mesh, it's much more difficult. I will talk about that also this week. And it's a major challenge. And it's also a major difference. When you want to go from this world to that world, the jump is not simple. It's actually, you need to rewrite another code. So as I said, DNS will be performed in this kind of boxes, which are all nice and good, except they are much too small for what we want to do. You can do DNS in many cases, and if you look at most recent DNS, you will find out that they are all in unconfined cases. This is, for example, a growing flame, 3D ignited in a turbulent flow. This is a jet flame published in the symposium. Here you inject fuel here, but again, the flow is unconfined. This is another one coming from Bell, I guess, Bell's group. Yeah. And again, you can recognize the simplified geometry so that you can put here a lot of chemistry and a lot of details on the modeling, but a very simplified geometry. Same here, I think this is a paper by Jackie Chan's group at Sandia, where you have a very complicated flame, but again, always a very simple geometry. And now you go to this kind of geometry here. This is a swirler, Turbomeca engine. And then right away, here you need another type of code. Okay? And I will talk about this tomorrow probably. I mentioned also optimization. The fact that it's not only about running the code, but being able to run multiple versions of the code, multiple geometries to optimize these things. And that's a big issue. And a few words about quantification of errors. As I said, the way it's done today is the following. You have a combustion chamber here, and behind it you have a turbine. And the people from the turbine ask the people from the combustion department, can you guarantee that the temperature will be right and the turbine will not die? So the combustion people say, well, the temperature at the outlet here will be 1400 K. So the guys at the turbine, they say 1400 K, okay, let's take margin. Let's make it 1600 K, just to be sure. These numbers are wrong, okay? I won't give you the real numbers. So they take margins all the time. That's what engineers do. They do a computation, and then to be safe, they multiply it by 1.2, 1.4, or 2 sometimes. But now, of course, as the time goes by, you need to improve your performances. You need to be better than your competitors, so you need to reduce the margins. If you reduce the safety margins, you have to wonder if the precision of what these guys from the combustion department gave you, if it is good or not. So when these guys in the combustion department tell you, for example, the temperature at the outlet of my turbine will be 1600 K, you want to know how precise this number is. That means, does it depend, for example, a lot on the flow parameters? Does it depend a lot on the geometry changes? Does it depend a lot on the coefficient you use in the K epsilon model? In other words, if you tell me temperature is 1600 K, can you give me exactly the margin of error? Because of course it controls everything afterwards. If you get this number wrong, then the engine will simply not work. And that's really a worrying problem for industry. And more we see industry asking for this kind of tools. This kind of tool has been available actually in the kinetics community for a long time. It was called sensitivity analysis. For example, people were computing laminar flame speed, and they could tell you the laminar flame speed of this flame will change by 10% if you change the pre-exponential constant of reaction 224 by 10%. You can do that in these simple cases. It's already complicated, but you can do it. But for 3D flows, it's actually a big challenge today. So during this course, we will discuss turbulent combustion, and we will describe the code that are used for turbulent combustion. And I don't want to do that without first discussing theory. If the idea would just to be take a code from a commercial company and just run it, you wouldn't need to be here. Okay, you would just push the button. The nice thing about combustion is that this never works. I've seen so many examples of people taking Fluent, running it, and getting completely stupid results. It's real fun, actually, to watch. And the point is you need to understand what you do. And to understand what you do with this big code, you need to go back to theory. That's the only way to do it. I want also to discuss what I will call complexities in combustion. Unfortunately, when you are doing a PhD on an academic flame, it's a little bit different from what's going on for the engineer who is trying to design a real engine. So I want to show you the difference between the different flames and the different CFD approaches that you need. What I call complexity is to go from this kind of systems, which are used in laboratories where you have a very complex chemical system, that's true, but you have a simple geometry, a simple flow, and you look only at the flow. You don't have to worry about heat or acoustics or anything like this. But when you go to industry, this is not what they want to look at. They want to look at this animal. And this one is another game here. And our challenge today is we have to keep doing that, but you need to prepare this, you need to be able to do that. Of course, you will still have complex chemistry. That's obvious, the chemistry doesn't change, but now the geometry obviously is complicated, the flow will be complicated, and you will need to do multiphysics, you will need to do acoustics, heat transfer, vibration, and all these things. So how does that go in a hierarchy of code, if you want? You start with the simplest tool you can write. Many of you have used it probably. It's what we call zero-dimensional flames. PSR is one example of such code. It's basically a box where you put fuel and air. There is no dependence on space. There's just a dependence of time. And you just integrate these two equations. There's only one temperature. The temperature in the box, the fuel mass fraction, all the species mass fraction in the box. And you integrate them with time. To do that well, you need only kinetics, you need a kinetic scheme, and you need thermochemistry, data, CPs, enthalpy, etc., etc. That's okay. And most of us can do that actually with existing code. The way it works is that you start initial time. After a while, the temperature will go up. You measure an ignition time. You can plot the ignition time versus the temperature. And this is a standard tool. All of you probably have used it. You can have that in open source codes like Computational, or you can buy it from Chemkin or Cosilab or places like this. Now, the next step is to go 1D. As soon as you go 1D, you need to add transport, molecular transport. And then that requires to do some kind of flow situation. And for the 1D strain flame, there's an approximation which allows you to solve it almost in a 1D framework here on the axis. And you impose the flow rate. And here you can solve this problem and do a lot of things just with this setup. And a lot of labs are doing that today. Then you can start worrying about a flame which is still laminar, but not a simple strain flame, but multidimensional. Typically this kind of flame, and then you need to start talking about fluid mechanics. That gets a little bit more complicated. And then you go to turbulent flames. So typically what you find in TNF workshops. So those are unconfined turbulent flames. So on top of all that, you need to add some description of turbulence. And that's where things get interesting. Already here, you can spend your life on this question, okay? There are groups, typically the Sandia group, has been exploring this problem for a long time, and even today predicting a jet like this one is something quite difficult. But still, you are not at the level that you need for applications. Applications, in many cases, include a lot of radiation. So if you go to an unconfined flame which is sooting, like this one, you need to add a model for radiation. You go and talk to the people who write radiation models. The cost of their model is larger than everything here. These guys are doing very expensive computations, so you need to simplify their models if you want to include them into a combustion model. And after this point, you have to forget simple geometries, okay? Everything which comes now has to be written in, with a code which can handle complex geometry. And the first problem you will have is just to be able to have a high order scheme with a complex shape for the geometry. So right away, you will have acoustics problem. Here, this is an injector. You can see the waves here propagating. As soon as you close the box, acoustics come into the problem. In an unconfined domain, if you make noise, the noise goes away. You don't care about it. But if you are in a closed box, the acoustics are going to be not a problem, but you have to care about them. Then, of course, as I said this morning, you have to care about heat transfer. The main problem you have in industry, if you confine the flame, you need to keep the walls alive. and typically you need to cool them. This is an helicopter chamber here from Turbomeca again. All these small things you see here are holes. We call them effusion holes. They are used, this is the outside of the chamber, some cold air will enter here through these holes and cool the walls there on the inside of the chamber. Without this thing, the chamber will die in a few seconds. So here, okay, combustion is important, but cooling becomes even more important. So you need to worry about heat transfer right away. Then these walls can move. That makes things even more interesting. This is an example of a solid rocket booster for the Ariane engine, and you can see here this part here, which has to be, it's a solid part, starts oscillating and starts coupling with the flow and producing additional instabilities. So you might have to worry about coupling your code with a code which does moving meshes and coupled with the structure mechanics. At this point, and this is a very important statement actually, is that the codes that you are going to use for practical applications are like a chain. They are as weak as the weakest link in this chain. So you don't want to, if you have to build all these things, you don't want to focus on the link that you like. You want to focus on the weakest link here. And this is what makes sense. It's always very difficult to appreciate where the weakest link is. Most people see the weakest link in what they do so that they can get funded to do it. It's typically kinetics expert. They will tell you that you need all these kinetics to do all this. But in practice, it's not clear, you know, because you have other problems that you need to solve, and the weakest link is not always at the same place. Because, for example, if you get in this room a guy with a CFD expert, he will tell you, forget about that. What you need to do is to worry about the mesh type, the order of the scheme, the time integration, the boundary condition, the fact that your code has to be massively parallel, that you have to be able to maintain it. You have to write it in C++ or Python or whatever, and that you need to be able to couple it. And then they will discuss, you know, if it has to be finite volume element, DG method, or finite elements, whatever. And they will write a code for combustion without ever talking about combustion. But still, in the end, we need to put all these ingredients together, and even that one. If you want to optimize this code, or if you want to do data assimilation, you might have to write the adjoint of the code. I don't want to talk about adjoint today, but let's say that, again, depending on your background, you will find out that writing a big code for combustion is a complex task. So I have a recommendation here, which was given to me when I was your age, and Peter O'Rourke was the guy who wrote the Kiva code a long time ago. Probably some of you have heard about that. Kiva is actually still used in many places. And the first line in Kiva was saying, don't be a perfectionist, which means basically don't focus on one element only in this chain, you know, because you have to account for all of them. And that's a very important statement. And it means also that sometimes in turbulent combustion you have to accept that you do things in a way which is not as rigorous as the specialist would do, but you have to do it because it's the only reasonable way to get it done. So it seems like a simple statement. You have to focus on the weakest link. The question is, where is the weakest link? Well, it depends. I just want to give you an example of, again, why you need engineers who know about combustion to do these things, because it's tricky. This is the example of cryogenic combustion in a rocket engine, where you inject hydrogen and oxygen. And if you have to compute a system like this one, and you're an expert in combustion, you know that combustion of hydrogen with oxygen is so fast that you don't need to care about chemistry. You could say it's infinitely fast chemistry. And if you say it's infinitely fast chemistry, the modeling and the way you write the code is going to be much simpler, because right away you know it's infinitely fast. It makes your life much easier. And you can do that. And you can sell your code to companies, and you will have good results, because all these frames will always start here. Combustion will always be stabilized here, because as soon as the molecule of hydrogen sees a molecule of oxygen, even in these high-speed flows, they burn. That's fine. But then you go to these guys 2 or 4 weeks later, to 4 years later, and they tell you, no, well, we want to replace H2 by CH4. That means, like the Russians do, you want to burn another gas, you know, or kerosene maybe. Now, by the way, if you have followed courses on chemistry, you know that CH4 is not going to burn as fast as H2. Actually, it's going to burn much more slowly. and the assumption of infinitely fast chemistry is going away. So the code that you solved 4 years before, which can do infinitely fast chemistry, is going to fail here. And it might lead actually to a much more difficult problem. In the same geometry, same conditions, much more difficult with methane than with hydrogen. And again, if you're an engineer fresh out of school, you don't know these things, but you will find out that in the end it won't work with CH4. And you will have to explain to the end user that actually H2 was easy, but CH4 is not. So then if you want to go to a case like this one, when you have H2 and O2 with finite weight chemistry, well, you will find out that the code to solve this thing is getting much more complicated. Okay, that's all I wanted to say for the introduction. I just want to ask you a question here. Could you raise your hand if this is going too slowly for you? A few guys who are... Okay, 5%. I'm not going to increase the speed too much, because the other guys are going to complain. If, should I ask if it is going too fast for someone? Not yet? Okay, so let's move now to this basics. The only thing I want to do here is to recall a question?
Yeah, not on this, but on the last slide where you kind of had all of the different components of the simulations.
Yeah.
And I guess, like, we're from an experimental group, and it's always funny, I mean, I guess this is kind of half comment, half question. It's always funny to see that the simulation guys seem to try to add, more and more blocks and more, stack it up and make it more complicated when the experimentalists try to make it as simple as possible. And so I guess what I'm, generally speaking, to make the interpretation easier. So what I'm wondering is, like, from your perspective, in the future, is the idea with all of these simulations to continually add more functionality based on your increased computational speed? And do you run the risk of being so complicated that your results become difficult to validate? Or are there people looking at individual specific, for instance, methods of simulation or areas of, where you can simplify and still get most of the result out?
We've been there before. I think there's quite a large number of methods which are simplified methods. But what we find out is that for many problems, they are not sufficient. So the trend today is really to incorporate much more physics into the simulation codes. I think it's just no way to escape that. The fact also that you get all these big machines to do it is really showing that we should do it. Now, you're raising another point, which we've seen actually. I'll give example probably Thursday. We've been able to mimic experimental results with simulations, and then we were stuck because they were just giving us the same result as the experiment and nothing more. And that means that the fact that you're able to mimic an experiment is not enough, even with a simulation. And what you do after that with the simulation to understand what's going on isn't clear today, because we are not there in many cases yet. But of course, the comparison with experiments remains critical. It's also one reason why we feel that we shouldn't have 99% of the people doing simulations. We need people doing experiments badly, because I wouldn't trust, wouldn't fly in an aircraft which is fully simulated. It's probably dangerous. Okay, so most of you, I think probably all of you, have followed the courses of Moshe Matalon on combustion theory. I just want to recall the results which are useful either for CFD or for turbulent combustion models, because you might have forgotten them since last year. So I will just remind you of the equations we're going to solve, talk about premixed flame, diffusion flames, and about other flames. And I will go extremely fast on things I consider you should know, and focused on things which are more controversial or more complicated in practice. First thing is something probably you did not realize, is why do we talk about laminar flames since we are interested in turbulent flames? Well, the idea here is that there are first things which do not change whether the flow is turbulent or laminar. If you mix fuel and oxidizer, for example, the outlet temperature should be always the same. It's just thermochemistry. So it makes sense to start, looking at this problem without the complexity of turbulence. Then there is a second thing, is that we all more or less have this flamelet intuition idea. What is the flamelet idea is that a turbulent flame is actually nothing else than a superposition of a lot of small flame elements, which we call flamelets, and that each of these small elements here looks like a laminar flame. And right away, when you say that, people say, oh yeah, it makes sense. But well, it does not necessarily make sense, okay? There are many reasons actually where we see that this assumption might be not that good. But again, why do we do it? Well, because it was the only thing we could do. It's a good way to start. So, it could be a problem. I will show you multiple examples where turbulent flames are different. I just want to describe one, which is this question of the Lewis number. The Lewis number is a way to measure the diffusivity of species. And we know that the Lewis number is extremely critical and very important for laminar flames. You've heard about that, for example, to control thermodiffusive instabilities. The Lewis number of the deficient reactant is very important. Now, interestingly, when you go to turbulent flames, species are not transported mainly by molecular processes, but they are transported by eddies. And eddies don't care about species because eddies just transport the mean flow. They don't discriminate between species. They will not carry H2 and leave CO2. That means that in a turbulent flow, which is dominated by a lot of eddies, normally everything diffuses in a turbulent way at the same speed. So the Lewis number that you should use if you study a turbulent flow should be the same for all species. But for a laminar flow, it's not the case. So there is here a big problem when we go from laminar IDs to turbulent IDs. What should we use for transport? And the literature today is full of examples where people say when we go to turbulent flames, we should just set all Lewis numbers to unity, and it works better. But there is no real justification for that. And of course, if the regime is intermediate between laminar and turbulent, what should you do? Should you use the laminar diffusion coefficient, or should you go to all coefficients are equal? So that's the kind of controversy today which makes your life difficult. Okay, conservation equations. We are talking about a mixture of species. We suppose that the gases are perfect. Just a word here. Except if you're doing rocket combustion at 120 bars or something like this, this assumption is okay. You can use the state equation, classical perfect gases. If you want to do rocket combustion, then you need to go to supercritical equations of state. Probably most of you don't care about that for the moment. The state equation is just written like this one. This is the mean molecular weight. The mean molecular weight, just a comment here, the mean molecular weight can be computed in an intuitive way as a weighted sum of the individual weights multiplied by the mole fraction, and not by the mass fraction, okay? I see sometimes in codes people writing W equals sum of the YK WK, okay? No, if you want to use mass fractions, as we do in most codes, it's 1 over W, which is equal to that. You have the really classical definitions, mole fraction, mass fraction, molar concentration. Molar concentration, in most codes, you can forget them. Codes will work either with mass fraction or mole fractions. The stoichiometry, you've seen it before. It's just a definition here. I don't think you need to elaborate on that. This is usual stuff. Let me go right away to the code. Okay. Some of you, but I've seen that not many of you, may have studied classical aerodynamics around an aircraft. If you study classical aerodynamics, you need 5 variables for the 3 velocities, and then for 2 thermodynamic variables, pressure or temperature or enthalpy or entropy, what you want, and density usually. So you need 5 conservation equations. As soon as you go to combustion, instead of 5 variables, you need to add all the species. And n here is the number of species. I've put n minus 1 because the sum of the mass fractions must be equal to 1, so you can cancel 1 if you want. N is large. So you see that when you take a code which can do flow around an aircraft and you want to transform it into a code which does combustion, you need to add a lot of species here. And we're going to need 5 plus n minus 1 equation. Where does this equation come from? Well, it's the same you have without combustion, then you need to add continuity for the species. The continuity equations, you've seen them before. You have here the diffusion velocities, and here you have the reaction rate. The sum of the reaction rate is 0 because for the moment, mass is always conserved with chemistry. We don't do nuclear reactions here, so we have no problem with this one. And if you sum all these equations, you should find this one. Okay, that makes sense because the continuity of the total mass must be the sum of the continuity of the individual equations. I want to spend a few minutes discussing this issue because, as you will see, again, I see a lot of people writing codes in combustion that don't conserve mass because it's easy to get get wrong here. That means if you want to satisfy this equation, you need to have the sum of the yk multiplied by the diffusion velocity equal to 0. That must be built in. How do you find the velocities, the diffusion velocities? Well, Moshe has talked about it. You need to solve this equation here, where basically at each point and each instant of your code, of your flow, you have the velocity, the diffusion velocities here. Those are the mole fraction. This is the binary diffusion coefficient. This is the gradient of the mole fraction. Those terms in most cases can be neglected. For example, the gradient of pressure here, you have limited effect. And this is the force, the volume force, you can forget them. This equation leads to a matrix to invert. If you think about this, you know, it's implicit in VK here. So you can write this as a matrix, and you have to invert this matrix at every time step, at every point. We normally never do it. Okay? Very few people do it. You do it in certain 1D codes, but in a 3D code, no one does that. We use simplified forms for diffusion. There are two of them. The most famous one is the Fick's law, and that's the one that Moshe discussed last year. And there's a second one, which is Hirschfelder's. And you look at these two things, you'll see it's about the same, except that this one is using the gradient of the mole fraction. This one is using the gradient of the mass fraction. You can prove that this one is the most accurate. That means that if you need to use a velocity for an expression, a simplified expression for diffusion velocities, you should use that one. So in this expression, if you look here at this one, you have a dpk, which is a binary diffusion coefficient that you can have from molecular theory, gas dynamics. Here you have a decay, which is not the same. The decay, actually, you can build it again from theory, and it looks like this one. It's a composition which depends on the binary coefficients and on the local composition. So it's not constant. It's not a given value. You have to compute it again at every point and every time step. In general, the decays are different. Okay, the small molecules and the big molecules won't have the same decay. A good way to look at the problem is to normalize the decay by the diffusion of the heat. This is how you form the Lewis number. So there is one Lewis number for each species where you compare the decay to the heat diffusion. The reason we do that is that even so the decay is changing and the heat is changing, the ratio of the two is not changing that much. This is a plot, for example, of the diffusion coefficient, the Lewis number, in a premix flame. So here you will have the cold gases, and here you will have the burnt gases, and at each point we compute the Lewis number of the different species. And you see that the Lewis number of hydrogen, for example, is almost constant from the fresh to the burnt gases. This is OH, H2, etc. And you see that Lewis numbers are less than unity for small molecules. It means that these small molecules are able to diffuse better than the heat. And the big molecules, they have more problem to go through the other molecules, and so they diffuse much more slowly. Now, the trick is not to use different Lewis numbers. The trick is to realize that if you use the simplified form, if you replace here these velocities by this expression, then you may have a problem with continuity. Because if you sum all these things, you will end up with a term here on the right-hand side, which is written like this. And if you look at this term, it's not zero. If you don't do something special, you cannot put the dk or the wk outside of this sum here and have something which goes to zero. And that means that if you write a code and you put different Lewis numbers and you don't do anything special, you're going to lose mass or to gain mass, which is, of course, something you cannot do. So how do you fix this problem in most codes? Well, you change, instead of having this expression for the diffusion velocity, you add a correction velocity, Vc. And then you put that again into the species equation and you sum them again, and you will find out that the global mass conservation now has this term on the right-hand side, and you can cancel that term just by choosing the correction velocity. And when you present it like this, it looks like a recipe, but you can actually prove, and it's done in a book which is quite difficult to read, but I give you the name anyway, a book by a guy called Ern and a colleague called Jovan Gigli. It's a full book where they only look at diffusion velocity expressions. And they prove that this one is the most precise approximation of the full diffusion matrix. And so it's the right way to do it. which means that basically when you want to write a diffusion velocity in your code, you have to put here this expression and you have to add here this correction velocity. If you don't do that, you're going to have problems with mass conservations. You want to be careful when you use the code of someone else. It's a good idea to test if they did that, because it's unpleasant after 2 or 3 years of PhD to find out that you did not conserve mass. A simple way to do it is to compute a 1D flame and to see if the flow rates are the same at the inlet and the outlet. The momentum equations now, those are the same with and without combustion. So that's easy. This term is 0, this is the force. You can forget about that for the moment. This is the tensor for the viscosity. The only difference with classical aerodynamics here is that the viscosity in a flame changes like temperature, typically. It increases. So you just have to be careful to put here something which changes with temperature. Okay, the last one, but not the smallest problem, is energy. When you go to today, in most codes, you will find that every code is using a different energy equation. All forms should be equivalent, normally. In practice, it's not always the case. And also, you want to avoid being confused about one form of energy compared to another one. So I'm going to give you some example. The first mistakes which I see quite often is people get confused about compressible versus incompressible energy equations. And the second one is to talk about total versus non-total energy. So let me show you how to get those things. Most of that is summarized in the chapter 1 of the book here. The first problem is to know if you're talking about molar or mass. You could imagine that in this community, we would have for a long time decided if everyone should work with molar quantities or with mass quantities. Well, the answer is we haven't been able to do that. So typically, people will either normalize everything per mole or per unit mass. The chemkin community, the people doing simple chemistry, most of them work with mole fraction, mole quantities, mole enthalpies, molar enthalpies, and people doing 3D codes, most of them work with unit mass. And of course, the trick is not to get confused going from one to another. You go simply from this guy to this guy by dividing by the molecular weight, but you want to be sure which one you're using. And so in practice, depending on the code you have, you might have to fight with either molar or mass quantities. For the expression of the enthalpy, you remember it's the sum of the sensible enthalpy and the chemical enthalpies, the heat of formation. All these things are tabulated. You don't need to care about them normally. Just need to care that they are in the right unit for your code. And for the mixture of the enthalpy of the mixture is the sum of the mixture of each species weighted by the mass fraction. Formation enthalpies are tabulated, so you can just get them in books. Just be careful, whether they are mass or mole. This is a plot of the heat capacity of species. So this is the molar heat capacity. If you go to low temperature, you find here this famous 7½ for CPK. So this is this expression. The molar quantities at low temperature, low pressure. But this one is not true actually for a long, extended range of temperature. As soon as temperature is going up, you go away from these values, and certain gases, of course, are different. And you see how it's changing with temperature. It is definitely changing, but you will see that for theory, quite often you assume Cp is constant. I will tell about that in a few seconds. This is the same thing for mass. Of course, in mass, as you divide by the molecular weight, the light gases are very large values. I didn't plot hydrogen here. Hydrogen would be like 15,000 for CPK in terms of mass heat capacity. So an interesting question is, why do we care? Well, we do care if you want a code which has some level of precision. Let's say you want to predict temperature within 50 Ks, and you need to account for variable Cp. But for theory, no, we don't really care about that. In most theoretical models, what Moshe has shown you last year, we say Cp equal constant. We even say sometimes Cpk, all the Cp for all species are all the same, which is obviously wrong, but it doesn't have a lot of influence. When you do that, when you say that Cp is constant, you get wrong on the adiabatic flame temperature. You can either over-predict them or under-predict them, depending on if you take a large Cp or a low Cp. Of course, you shouldn't want to produce pollutants. because since pollutants are very sensitive to temperature and you get temperatures wrong, it's not a good idea. But the rest of the physics basically is captured by these theoretical models. And the simplification is so large, so interesting, that when you talk about theory, quite often you say Cp equal constant. Now, what about enthalpies? If you again come from the world of classical aerodynamics, you know two enthalpies, the CPT and the total enthalpy, where you add CPT and the kinetic energy. You go to combustion, unfortunately, it's a bit more complicated. The sensible enthalpy is not CPT, it's the integral of the reference temperature to T of Cp dt. Usually, you have an intermediate quantity here where you add the formation enthalpy, the chemical energy, if you want, to it. And then you can even add to that one the kinetic energy. And sometimes you see people using only the sensible enthalpy plus the kinetic energy. And depending on the code which you are using, people are maybe using one of these four, or they could also be using energies instead of enthalpies. So you can have 8 quantities in a given code. And of course, all of them will have different conservation equations. Note here that you go from enthalpy to energy always with this relation. This remains true in all cases. Note also, of course, that the Cp here of the mixture depend on the composition and on temperature. So it's a function of temperature and composition at the same time. So a good way to start deriving this equation is the total energy ET, which is here, because it has a simple expression. This is the general expression in a reacting flow. The only trick here is to recognize that the flux of heat is not lambda grad T, as most of us expect, but there's also a flux due to the fact that species, when they diffuse, do not carry the same enthalpy, same energy, so you need to correct it, this flux by this term. But apart from that, this equation is reasonably simple. The problem is when you go now derive all the others, this is what you find. Lots of them, 8 equations. All of them look the same, but they are not exactly the same. So my advice is if you write a code, or if you use the code of someone, make sure that you get all the right terms here. And as you will see, these terms, they all look the same. For example, in this equation, tau ij is in front of the gradient, and here it's inside. I see a lot of students coming to me saying, hey, it's not the same equation. I say, why? Because it's not the same variable. Make sure you're using the right variable. That's the source of a lot of problems in 3D CFD reacting flows. These things here, you don't need to worry about them. Volume sources is typically if you add radiation, and forces here if you have volume forces, but you don't have that usually. You've seen here that in these equations you have n reaction rates, one for each species, but you have only one heat release term. Just a good one about this one, this is what we call the heat release, depending on which side of the Atlantic you're sitting. Heat release doesn't mean the same thing. One reason for this is that I've shown you equations for energy and enthalpy, but a lot of people like to work with temperature. This is the equation for temperature. You can derive it like the others, and it has also a heat release here, but it's not the same as the heat release you have in the other equations. It would be too simple. So for example, for the energy, this is the heat release you have, and it's the sum of the reaction rates of each species multiplied by delta HFK0, which is the heat of formation. And if you're looking at this equation for temperature, you have a different heat release, which is about the same. You recognize here this term is here, but has an additional component here coming from the sensible enthalpies. One of my students spent 2 months trying to compare his results to data from Chemkin before he realized that heat release was not heat release. It's just, there's about 10% difference. So there is a case where these two heat release are equal. It's when you suppose that the CPK are constant, don't depend on temperature. Then you can prove that this term goes to 0, and these two heat release are the same. But if you're doing precise chemistry, you want to make sure that you get the right heat release when you want to plot it and compare it to someone else's result. The other thing is that if the CPKs are constant, there are other terms which disappear in this equation, and you end up with the classical temperature equation that you have seen in Moshe's course. Just the change in temperature is due to the heat release and the gradient of temperature, typically the heat flux. So we have these equations, okay? You could say, I just take them and plug them in the big code, and that's the end of the story. In practice, if you do that, it's not going to work. You need to understand what you do, and a good way to do that is to look at a few academic cases, simple flames, where you can see how these equations behave and understand what the problems will be in practice. And that's what I will do now using these two cases, the premixed laminar flame and the laminar diffusion flame. And again, many of these concepts will be directly useful for turbulent combustion. This is why I need to talk about them a little bit. So the premixed flame. The premixed flame is basically a wave where you have cold gases which are burnt by a front traveling in this direction, and it's 1D. And if you sit in the reference frame of the flame, it's even steady. So the problem depends only on space. So typically the profiles will look like this. This is the fuel mass fraction going from 1 to 0 in the burnt gases. The temperature will go up, and the reaction rate will be located here. And this flame has been the toy of mathematicians for more than 100 years. They've played all kinds of games there. I'm not going to do that. I just want to recall a few results. The first thing is that if you're not a mathematician, you can use a code to solve these equations. In this reference frame of the flame, you just have continuity of mass. You have the species equations, n of them, and you have the heat release term. You can plug that into one of these software. You can buy Chemkin if you're rich. You can get Cortera for free if you're not. You can ask Einspitch to get Flame Master. Anything you can do to solve these things. And you will get results. Typically, you have this kind of plots where you have the cold gases here, the burnt gases here, the flame thickness. You will have all the intermediate species. All of this will be working, okay? But it doesn't tell us much about what's going to happen when we go to turbulent flames. This is why it's very useful to keep simplifying here. If you keep simplifying things a little bit more, you are able to do things by hand. So what you do to simplify, you start by saying that there is a single reaction. I hope there's no kineticist in the room. When you tell them, I have a single reaction, they say, where is chemistry? Well, it's in single reactions. It's one step. Okay, we know there is no such thing in nature, but still, to do that, it's quite sufficient. We suppose that all the Lewis numbers are equal to unity. So everything diffuses like heat, including the fuel. So you end up with this set of equations, which is still a difficult set of equations to solve, but you give that to a good mathematician, he will do it for you. And Moshe is actually here, you can ask him. Just a way of how these things are done, you normalize the fuel mass fraction by its inlet value. You normalize temperature by the temperature jump here. So it's T minus temperature of the fresh gases divided by T of the burnt gases minus T of the fresh gases. And we'll use that quite often also for turbulent flames. That's what we call the progress variable, going from 0 in the fresh gases to 1 in the burnt gases. You can show actually that with the assumptions I've just described before, these two quantities are related. If you have one, you have the other. The sum of these two is 1. It's like a conservation of mechanical energy, if you want. Either you are cold and you have some chemical energy, or you are burnt, y goes to 0, but everything is in the temperature. So you can solve for only one variable now. Typically the temperature, you end up with this equation, which is an equation where the only unknown is the temperature. And you can see it has a rather interesting heat release term here, but you can compute it. And if you want to solve that, then you need to go talk to a good mathematician. I don't want to do that. I just want to summarize the results. Most of the results are based on the observation that the reaction rate term has a very funny shape. It's a very nonlinear term. Fortunately, in combustion, when you are cold, nothing happening. In this room, you can mix gas and air. Nothing will be exploding if no one is smoking. Then if you heat this room to 400K, it will be the same, 600K, 800, and at some point, reaction will take place. And when it will take place, it will do that in a very nonlinear way. And it will be a very violent reaction in this zone. So what people coming from the mathematics point of view say is that they can split this region into a zone where there is no combustion at all, which is called the preheating zone, and a zone where combustion takes place. And you can scale all these things, and you can find ways to express the thickness of that guy and the thickness of this one. Now, you can even derive then from that an analytical solution, which is given in most books. And what this solution tells you is that the reaction rate will be organized in this way. The thickness of the flame will be given by this expression. So that's an interesting expression. You can rephrase it that way if you want to remember it. It means that the Reynolds number of the flame is unity. That means that the the flame thickness multiplied by the flame speed divided by a typical diffusion coefficient is equal to 1. This expression is true in many other fields of physics. A shock wave, for example, you have the same expression, but here you would replace the speed by the speed of the shock. In a flame, it means also that when the flame is fast, it is also thinner, okay, and vice versa. So that's a useful information. If you have a code which is working for a flame and you want to compute another flame which is faster, well, you know it's going to be thinner. You need more points. If you don't know that, you know, you have to fight your way through before you realize that you have a problem here. Now, the speed itself depends on the expression you pick up for the diffusion coefficient of heat. Depending on which coefficient for heat you take here, something constant, something depending on temperature, you will have a different flame speeds. All these expressions of flame speeds are valid, and I don't want to go into the details. I just want to get one generic result here, which is the following. In a problem like this, a laminar flame propagates at a speed which is a function of the heat diffusivity multiplied by the constant of the kinetic to the power 1/2. Okay? So it means, first thing, and that's different in the detonation, it means that if you have no diffusivity in your gas, there will be no flame. Okay? The flame to propagate needs diffusion. And it needs, of course, chemistry. That's clear. But it means also that if you want to go faster, some people do that in codes too, they want the flame to go 2 times faster, they increase the kinetics constant by 2. Well, the flame will accelerate only by a factor of square root of 2. Theory tells you that, and it's very well verified, very well easy to check in real codes. And so it means also that to propagate this flame, you need to account both for diffusion and reaction. If you get one of these two wrong, then you will have problems when you look at the results of your code. In practice also, I want just to mention a mechanism which will be important for DNS. This is how flames are. You can imagine that flames are propagating that way. At an initial time, you have a temperature profile like this one. Suppose you have no reaction for a certain time, this profile will diffuse in both directions. So these gases here will be colder, and the gases here will be warmer. And then what combustion is doing for you is that the gases which are in front here, they will react, and they will come back to the same shape that you have here, but propagating in that way. So you see how diffusion is necessary to heat up the gases in front of the front, and then reaction is necessary to bring them to the adiabatic flame temperature. Now, before we have another break, I just want to introduce something which we will use very much for turbulent flames. It's a nice property of these flames, which was also mentioned by O'Rourke probably 40 years ago. And O'Rourke said, look at this expression of the flame speed here. There's something I can do about this, is that if I multiply the diffusion by a factor f, and I divide the kinetics constant by a factor f, and again, if there are kinetics experts in the room, I apologize for them. You shouldn't divide their constants. But you get the same flame speed. And if you look at the flame thickness now, if you do what I just mentioned, you find the flame thickness will increase by a factor f. So what this means is that you can take a flame like this. This is the flame equation. Let me just show you the flame equation. That's the original flame equation. That's the modified one. The only thing you do is you multiply by f here and here. Okay? You have less reaction, you have more diffusion. This flame will propagate, these two equations will propagate flame exactly at the same speed. That means that this is the initial flame, for example, and this is the second flame. These two flames move exactly at the same speed. And here again, I am taking the point of view of a numerical guy, because resolution will be a big problem. Why do we do that? Well, you see here, we have a method to propagate a front at the same speed, but reach much more points. This is, for example, the heat release. This is the unsecond flame, and this is the second flame. Obviously, for the red curve, you need much less points than you would need here. So a thickening flame front is one of the things we do in combustion when we are desperate for resolution. You've seen that many of these flames may be, I don't know, 10, 100 microns thick. If we need to put points in this thickness, we are not able to mesh all the geometries we need. At the same time, if you care only about the speed of propagation, why worry about the details of the internal structure? You can propagate the flame at the same cost with this kind of method. So that's a very useful simplification. If you probably some of you may have heard the code of Heinz-Pitch. This is a solution which has another possibility in the G equation. The G equation, instead of making the flame thicker, you just bring it to the zero thickness, and you say it's just an interface. And basically, in the community today, you have these two possibilities. Either you make the flame completely thin, thickness equal to zero, the G equation model, or you make them thicker. And I will discuss that in the probably Wednesday to tell you the differences between the two methods. Okay, I think I'm going to stop here for the break, and when we come back, we'll talk about flame speeds again. Any question at that point? No? Okay, let's have another break then.